Thank you very much, Carsten. And before I start, I take on the technology. Can everybody hear me in the back? Yes? In the back? Yeah? So? Can you maybe turn the microphone up? Because I don't think I can speak much louder than that. Better? 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 No, I don't think it's
apparently it's not super sensitive. How's that?
Better? Still? No? Better? Okay, I'll try my best. So it's a great pleasure and a privilege to be able to kick off that now famous historic school of Penn State Bioinorganic summer program. And I know that Carsten has organized it such that he always has the worst talk in the beginning that nobody wants to hear. And I'll try to not live up to that. But so what we want to do here is to lay some foundations that hopefully you find useful not only as a part of the teaching program but also later in your practical life. And so I want to start by reminding everybody about a third of all enzymes are metalloenzymes, and it's universally true whenever nature had a complicated chemical problem, it chose transition metals to do the job. So whenever we have a really hard bond to crack, whenever we have a really complicated reaction to catalyze, when we want to transfer electrons over larger distances, nature's choice universally were transition metals. And by now we know very many enzymes that have transition metal active sites or electron transfer sites, even structural sites. And we know their crystal structures, but does that mean that we know the mechanism? I know that in protein crystallography there is a certain suspicion that as soon as you have solved the structure you know the mechanism, but that's not true. And it's only the part, I know that seeing is believing. It's right, Ollie? Yeah. But you shouldn't believe everything you're seeing. And more often than not, you really need the combination of the crystallography with the spectroscopy in order to figure out how the mechanism really works. And that, of course, begs the question, as soon as it comes to spectroscopy, you're looking beyond the surface. You're looking beyond the geometric structure, the one that crystallography sees. You look into the electronic structure of the transition metal. And that means you have to have at least a cursory understanding of what transition metal electronic structure is, and that is what I try to convey to you here in the lecture on ligand field theory. So if we zoom in a little bit, these are typical metal sites and enzymes. All of them are iconic and have played a huge role in the development of bioinorganic chemistry. That is the electron transfer site, and plastocyanine is the copper that cycles between copper 1 and copper 2. That is a P450 active site, the proverbial enzyme to activate CH bonds. That's the famous iron molybdenum cluster in nitrogenase, the active site of methane monooxygenase, or the infamous water oxidizing complex of photosystem 2. And these are about the hardest reactions you can possibly do. And especially if you think about dinitrogen activation, that is, dinitrogen is the single most inert molecule on the planet. That's why it's most of our atmosphere. And if you want to crack it open in an industrial Haber-Bosch catalyst, you have to apply high temperature, big pressure, and then it just goes. But nature does this at room temperature, neutral pH, and ambient pressure. So that is amazing, and we really want to understand that. And what we have learned the hard way in bioinorganic chemistry, the way it doesn't work, is that we try to build low molecular weight coordination compounds that look similar and then hope that they perform the same function, because that really doesn't work. So the understanding needs to proceed beyond what you see here in front of you, beyond what the geometric structure tells you. All of the secrets are in the electronic structure. And the electronic structure, that is the subject of ligand field theory. So when we start to take a look into coordination chemistry, we should go all the way back to the beginning of the 20th century, where the seminal work of Alfred Werner first defined the playground of transition metal chemistry. And he, without having any theory of it, he prepared hundreds and thousands of transition metal complexes. This is one of the very famous one. And he got the structures, all of them right, by the sheer power of deduction without having any theoretical background. So chemists have been having Lewis structures forever to talk about organic molecules. And I think the Lewis structure is like the single most important concept in chemistry that lets you understand chemistry. And all of you who have studied organic chemistry know how powerful it is and how much you can, on a paper, manipulate molecules and think about reaction pathways and all of those things, because you know how to push electrons around, and you have the plus I effect and the plus M effect and all of these things. And in coordination chemistry, you have none of that. There aren't any Lewis structures for coordination complexes. So the language that organic chemists speak is the language of Lewis structures, but the language that inorganic chemists speak is the language of ligand field theory. And this is the language I want to talk to you about. But of course it proceeds way beyond just metal active sites. You have transition metals all over chemistry and also technology today, where they play super important roles. So here we are focusing on metalloenzymes, but I wanted to alert you to the fact that there is a huge world outside where transition metals are absolutely critical. So everywhere in homogeneous catalysis, transition metals are absolutely crucial. They are typically not the same ones that you are finding in enzymes. It's more the second and third transition row, but it's absolutely critical in homogeneous catalysis. And then in heterogeneous catalysis as well, where you have transition metal oxides that are amazing industrial catalysts, or MOFs that play a very important role in catalysis. Then you have it in all kinds of technological application. You have like rare earth luminescence that is absolutely beautiful. The huge field of single molecule magnets that is promising for quite a while to revolutionize the miniaturization of switching devices. And you have really interesting fields like metal radical interactions. And here you absolutely cannot understand anything without diving deep into electronic structure. So hopefully that is motivation enough to study that a little bit. And I will call on the founding father of our foundation, Max Planck. This thing is not working, but and he said, "The only source of knowledge is experiment. The rest is poetry and imagination." And think about it, that is a very powerful sentence, that it means what is
You want to?
Oh no. No, it's fine. The pointer works. Okay. It's just the clicker doesn't work. Then it's so what that means is we have, as scientists, the facts that we can observe. So this is a factual material we're working with. And then, of course, we need a language to talk about it. We need pictures in our heads in order to be creative. And theory, of course, has a double role. And one of the roles of theory is to connect the observables, the numbers, whether you measure a G value or a dipole moment or a molecular weight or something, and you need to connect that observable by theory to what you have measured. But then theory has a second role, and that is to create concepts that aren't observable, languages in which we can talk about and be creative. After all, like all molecules are subject to the laws of quantum mechanics. Now, the laws of quantum mechanics are complicated, and if we only had those laws of quantum mechanics to communicate, we couldn't talk about it, right? Because there would not be any intuition emerging from that. But we need simple intuitive concepts, and that is the poetry and imagination that Planck is talking about. So when I talk about ligand field theory, I will put that in the middle of the exposition, because you can get to a very illuminating cycle that lets you close all the way the subject from geometric structure, so that depends on the nature of the ligands and the d-electron count, local geometry, to the electronic structure. So there is an intimate relationship between the geometric structure of a compound and its electronic structure. So we talk about spin states and excited multiplets and so on and so forth. And of course, it's the electronic structure that is reflected in the spectroscopic properties. So spectroscopy, really what it is an experimental way to study electronic structure, right? And so here is the link between the experiment and the theory. And there is no better link between electronic structure and reality than spectroscopy. And finally, of course, it's the electronic structure that finally dictates the reactivity. So in principle, if you speak the language of ligand field theory, you can close the entire cycle. You can go from geometric structure to electronic structure. You have the spectroscopic properties, and then you can go back to the reactivity. And that is extremely powerful. And during the course here, you will learn a lot about various spectroscopic properties. But remember that like all of these things are intimately related, and all of these things, like one is reflecting on the other. And so if you try to make all these connections, you have a very powerful language at hand. Now, what is ligand field theory then? Ligand field theory is a model, and a model that applies to an entire class of substances. And that is something that is fundamentally different from, say, the theory of quantum mechanics. So the quantum mechanics lets you take a single molecule and calculate it in a given geometry, and if you solve the Schrödinger equation, you know everything that quantum mechanics allows you to know about the molecule. But it is that one molecule in that one conformation. And when you change a methyl group, or you like move a bond a little bit, then it's an entirely new problem, and you start from scratch and you don't know what the outcome will be. But that is not what a model wants to do. A model wants to create a simple language in which you can talk about an entire class of systems, and that is what ligand field theory does. The ligand field theory is recognizing that all molecules that have a D2 configuration have certain things in common. And this is what the model wants to clearly expose. As such, a model is always wrong. It wants to be wrong, but it wants to be wrong in the right way. And that is a really important thing to understand, that like we're focusing our attention on a small part of the world that we observe here, and we create something that lets us talk about it in an entire class of systems. So as such, that ligand field theory is not an ab initio theory that lets you predict the properties of a compound from scratch. That is what quantum chemistry gives you. Yeah, but this is not what ligand field theory gives you. And ligand field theory is also not a physically rigorous treatment of the transition metal electronic structure. So I will argue later that if you take ligand field theory like literal, and you evaluate everything the way it is written down on paper, you get absolutely ridiculous numbers. But still, there is enough that's worthwhile taking from ligand field theory that has a bearing on reality. So now let's talk a little bit about many electron atoms and the Aufbau principle, and I'm sure you have all seen that in the introductory courses on general chemistry, that the periodic system of elements is built according to the Aufbau principle, where you have the atomic orbitals of the system and you start filling electrons from low energy orbitals to high energy orbitals. So when we hit the transition series, then of course we start filling the 3D shell here. And it is the open 3D shell that is probably the most complicated electronic structure that we have in chemistry. So to some extent it gets easier when we go further down to heavier element, and it's a whole lot easier in all of main group chemistry. But the toughest problems we have in electronic structure theory really arise in the 3D series. So I have to torture you a little bit, like for like a few minutes with some theoretical aspects, and I know that Serena will probably put up slides later, like showing me how I preach to the choir, because it's something that is so absolutely critical that you get that clear in your head. And I know that the majority of textbooks aren't clear to completely wrong in that subject. And that is the following realization. So atoms and molecules with many electrons, they exist in states. So a state is the overall state of all of the electrons in the molecule. And that can be characterized by 4 criteria. So the configuration, the electronic configuration, that is simply telling you how the electrons distribute around the available orbitals. So the occupation number of each orbital can be 0, 1, or 2, as you know, right? And so a set of these occupation numbers, that defines the configuration. And since these orbitals have a certain symmetry, there is an overall symmetry of the state. And I'm getting into that in a moment. And that is important because in transition metal chemistry, we often have either high symmetry or approximately high symmetry. And it's very common if you read the transition metal literature that you read term symbols, and then you need to understand what these term symbols are. Then, of course, electrons have a spin, and that is something that is quite odd, and it only exists in quantum mechanics. It's a kind of internal angular momentum, and in the EPR lectures that follow this one, you will learn a lot about it. So, but the spins of the individual electrons, they couple to a given total spin, and it's only and only ever the total spin that you can observe. And together with the total spin, there is a projection quantum number, the Z component of the total spin, and that you need in order to define a state. So basically, this is what defines a state, the set of occupation numbers, the total spin, its projection on the Z-axis, and the spatial symmetry of that state. I want to give you an example because these things aren't very clear most of the time. So let's take, for example, a simple closed shell molecule. Okay, so we have our orbitals here, and they're all doubly occupied according to the Aufbau principle. Now you make an excitation, and you excite an electron to go from one orbital to an empty orbital, then you create an excited state. And if the spins remain anti-parallel, you create a singlet excited state. But if you flip the spin in the process, you create a triplet excited state. So that means a one electron excitation in this case creates two states that you can observe, a singlet state and a triplet state. But it's getting more complicated than that. Let's say we have an open shell molecule that has one unpaired electron in its electronic ground state. Now let's make an excitation from a doubly occupied orbital to an empty orbital, and then we create an excited doublet state. So the ground state is a doublet, and the excited states, if we move that electron here, is also a doublet. But then we can do the same again, and we produce a quartet state by flipping that electron. But now there's a third state, and that third state is when you flip the electron here in the SOMO, and that also creates you a doublet state. So that single one electron excitation here creates three observable states. Okay, so you get the pattern here. There are very many more observable many particle states than there are elementary one electron excitations. And that is absolutely important to understand. You never, ever, not in this world, ever observe orbitals. Orbitals aren't observables. You observe states of the systems. Yeah? And configurations with several unpaired electrons generate several states. And if you get that clear, you understand transition metal electronic structure, because that is the absolute basis for everything that is happening in transition metal electronic structures. Yeah? So only the states are observables, orbitals are not, despite the fact what your organic chemistry textbook tells you, despite all the nonsensical homo-lumo arguments that you read everywhere all the time. Forget about all of this. Yeah. You know, I once had a math teacher, he said, like, you know, it's always great to discuss, but sometimes there's only one right thing, and that's what I say. I'm not that math teacher. Make up your own mind, disagree with me, but I'm convinced that this is true. Okay, so when we talk about states, then in atoms, we have the so-called Russell-Saunders terms, and I hope that you have heard about them. And these Russell-Saunders terms, they're characterized by an atomic term symbol. And the atomic term symbol is given by a capital L, that is the orbital angular momentum of that state, and a superscript 2s plus 1. And 2s plus 1, that's called the multiplicity, the spin multiplicity of the state. Yeah, so it gives you the number of magnetic sublevels that a given total spin S creates. And so in EPR, that's absolutely important because you probe transitions between these magnetic sublevels. Yeah, and so total spin S creates 2s plus 1 magnetic sublevels. And of course, you all know Hund's rules. So a given term with total angular momentum L is 2L plus 1-fold orbitally degenerate, and 2s plus 1 times 2L plus 1-fold totally degenerate. And for historic reasons, and only historic reasons, there is nothing to understand about it. So states with L equals 0, 1, 2, 3 are given the symbols S, P, D, F, G, etc. Yeah? Now Hund's first rule states that terms of a given configuration with higher total spin are lower in energy. That only holds for atoms, right? Don't transfer that to molecules. So it's only in atoms where electrons are distributing about a degenerate set of orbitals where the where the higher s is always lower in energy, Hund's first rule. And then within a given multiplicity s, terms with a given configuration and equal spin have the higher L lower in energy. That's Hund's second rule. And that gives you, like, there are big tables online, the Neese tables that list all of those multiplets that have ever been observed. So quite typically what you observed here are these line spectra, these very famous atomic line spectra. So these lead to like either absorption or emission lines that are extremely sharp, and they are very beautiful to look at. And for transition metals, there are very, very many of these states that can form. Let's give us two examples here, because it's important to understand ligand field theory a little bit down the road. So here we have our 5 d orbitals, and they're degenerate. And now if I put one electron in, I put it in with spin up. So the total spin here has to be, because there is only one electron, has to be 1/2. That means the multiplicity 2s plus 1 is 2. Now, I can put this electron here, or here, or here, or here, or here. So there are 5 equivalent ways to do that. And that means the L quantum number must be 2. And that would define a d state. So overall, the term symbol for that single electron in the d shell, that would be doublet d. And examples of that would be titanium 3 plus or vanadium 4 plus. Now, another simple case is the following, where each of these orbitals has one electron and they all have the same spin up. In this case, you have 5 unpaired electrons. They all line up. So the given total spin here is 5/2. That means the multiplicity 2s plus 1 is 6. And there obviously is only one way to do that, because if you wanted to move one of these electrons, you would need to flip its spin and you would come to a lower total spin state. So this is the only way to do it. That means the L quantum number must be 0, so you have a sextet S state. And that is very famously the case for manganese 2 plus or iron 3 plus, and that is the reason also why in the literature, the transition metal literature, you often have these ions be referred to as the sextet S type ions. Okay, this is simple, this is simple. The next simple case is if you have 10 electrons, so everything's fully filled. That is trivial. But the less trivial cases arise if you have a partially filled shell. And that is the case, for example, here with 2 electrons. And let's say we have 2 electrons that have both spin up. So the total spin must be 1. That means the spin state must be a triplet. But now if you count it out, there are 10 ways to distribute these 2 electrons over the 5 orbitals, both with spin up. And that means this is creating more than one L state. In fact, it's creating, if you go through the rules, and that would need a semester of physical chemistry, this creates then a triplet F and a triplet P term. So from this, there are 2 states that arise that are observable here in the line spectrum. Yeah? And examples would be here vanadium 3 plus or chromium 4 plus. And so that is what I wanted to tell. And now, obviously in molecules, the situation is quite different, because the total angular momentum is no longer a good quantum number. We say that the angular momentum is quenched in the presence of a ligand field. And so in the EPR literature, you read that all the time. So this one, the total angular momentum, that is no longer a good quantum number when you go to molecules. But you have a different quantum number that that takes its place, so to say, and that is the symmetry quantum number. And I guess that most of you have gone through a semester or two of group theory, and of course we can't do that here in the time that we have. So I just wanted to briefly brush over that problem in order to introduce the notation that we're using. So a molecule can be classified according to the symmetry operations that turn the molecule into itself. Right? And those can be rotations, improper rotations, inversions, or reflections. And the precise mathematical theory that classifies all of these symmetry operations, that's group theory. And the result of that analysis is that the electronic states can be classified according to the irreducible representation. So that is the symmetry quantum number I've been talking to. Now, of course, the orbitals have a symmetry, and that can be, and they transform under certain irreducible representations. And the overall state also has a symmetry. So in order to not get those confused, like what's one electron and what's many electron, a very convenient convention is to use small letters and reserve it for orbitals, so one electron level, and capital letters are always reserved for states. And now, according to the molecular notation of group theory, a T state only refers to a triply degenerate level, so capital T to a triply degenerate electronic state, or a lowercase t to a triply degenerate set of orbitals. E refers to doubly degenerate level, and A and B refer to non-degenerate levels. So the equivalent of the Russell-Saunders term symbols are the molecular term symbols, and they're given by 2s plus 1 superscript gamma, where gamma is then the irreducible representation, so the symmetry of the overall electronic state that we're describing, whereas 2s plus 1 remains the symmetry. So you see that we basically replace the total angular momentum L by the symmetry quantum number here. Okay, equipped with that, we can go back and talk about how our coordination compounds formed. And so in principle, it's quite simple. Then is transition metal ion is a positive entity, and a ligand that is either negatively charged or has lone pairs available to bond to the metal ion. So that is a delta minus here, and there is simply an electrostatic attraction. So if you have ethylene diamine, a very simple ligand here, you have that lone pair here at the amino group. And if you look at the electrostatic potential, it's negative at the places of the lone pairs, positive elsewhere. And so there's simply an electrostatic attraction. Now, a very, very important concept in coordination chemistry is the concept of a coordination number. And these are the most common coordination geometries that coordination complexes can assume. So if you have three contacts, so to say, between the transition metal and its ligands, you have the option of having a trigonal side, a trigonal pyramidal side, or a T-shaped side. That's quite rare here. For four coordination, you have a quadratic planar or tetrahedral side, or something that is in between, so a distorted tetrahedron. That's also quite common. For five coordination, you have a quadratic pyramid or a trigonal bipyramid as limiting cases, so they're related by so-called Barry pseudo-rotation. And for six coordination, you have predominantly octahedral sides. There are higher coordination numbers, especially if you go to the heavier elements, but these are the most common ones that you meet. Now, of course, these are idealized, but in enzymes, you still have approximate symmetry. You never have high symmetry in enzymes, that's clear. You can't, right? But you recognize the patterns, and that's why it's very useful to be aware of the properties of a given metal ion or given DN configuration in a ligand field of a certain symmetry, because there are properties that they still share with the high symmetry sites that you meet in coordination chemistry. For example, here in rubridoxin, that's an iron that is involved in electron transfer, you have an approximately tetrahedral site. Of course, it's not really tetrahedral because these sulfur-carbon bonds, they break the tetrahedral symmetry. But it's close enough to a tetrahedron that rubridoxin retains properties of a tetrahedral active site, and that's why it's important to study these high symmetry cases. For protocategoid dioxygenase, you have an approximate trigonal bipyramid. For tyrosine hydroxylase, also an iron site, you have an approximate tetragonal pyramid. For lipoxygenase and a million other enzymes, iron enzymes, you have an approximate octahedral site. So you see, you really find all of these coordination geometries. So now what we need to figure out is what is happening electronically to the metal ion when you put it into a ligand field. And so to remind ourselves, these are the shapes of the d orbitals, so that's similar for the 3d, 4d, or 5d orbitals. And it's useful to classify them according to how they behave with respect to the overall global coordinate system. So d orbitals have an angular momentum of 2, so these are L equals 2, and that means they have two nodes. You see here nodes are those places of where the probability amplitude is 0. And there are 5 of them, and they can be classified according. So first of all, you have the dz squared minus r squared orbital. That has that funny donut shape here, and along the z-axis it has that very pronounced lobe. And all of the 4 others, they look qualitatively similar, just rotated with respect to each other. That is the dxz-yz orbital, so that is in the xz plane. The dyz orbital is in the yz plane. The dx squared minus y squared orbital is in the xy plane, but has its lobe oriented along the x and y axis, and the dxy orbital is 45 degrees rotated relative to that and has its lobes located between those axes. So for those of you who haven't looked at these orbital plots, what we're plotting here is the so-called probability amplitude. So we take a certain function value, say plus minus 0.05, and then we draw like a surface around it. And the probability amplitude in quantum mechanics, that is not something that's directly observable, but the square of it gives you a probability density, meaning it's a probability of finding an electron that occupies this orbital at that place in space. So let's try to square that, then it will look qualitatively still the same. It will still have the nodes here, but of course the sign will disappear. Yeah, and that means if an electron occupies the dxy orbital, it has a probability of being found here in the xy plane in between those coordinate axes, but you will never find it like anywhere on the x-axis or on the y-axis. So that is the meaning of these contour plots. And that has, of course, a consequence when you put the transition metal ion into a ligand field. And of course, ligand field theory is a classical, typical physicist theory, and physicists hate chemistry. And so for a physicist, like there is a transition metal, and then there's all that chicken fat around it, and that we call the ligand. And that's why for a physicist, like the rest of the world looks like an electrostatic potential. And it's right. And so if everything looks like a point charge. And so let's try to be proper physicists here and forget about all this chemistry stuff, and just have the illusion that those ligands are just point charges. So like we take an octahedral side here, and so we have point charges along the plus minus z-axis, the plus minus x-axis, and the plus minus y-axis. Now I will make a probability, like a plausibility argument that you may or may not buy into. There is a mathematical backup for that. But now, given what I've told you about the shape of these orbitals and the probability of finding electrons there, then you will see that an electron that occupies the dz squared orbital on average has like a shorter distance to those negative point charges than an electron that's sitting in the dxz orbital, or the dyz orbital, or the dxy orbital. And so here we have a negative charge of the electron. Here we have a partial negative charge, at least, of the ligands, and that means there is a repulsion. All right? And now that repulsion is, of course, stronger for a shorter distance between two like charges. That means an electron in the dz square orbital is more strongly repelled by the ligands than an electron in the dxz or dyz orbital. And that means what the ligand field does is to lift the degeneracy of the 5 d orbitals that we have in the free atom and splits it into 2 pairs. And if you go through the proper group theory, then you will see that the splitting occurs such in an octahedral ligand field that the orbitals split in a T2G set that's triply degenerate, and that's the dxy, dxz, and dyz orbitals, and a doubly degenerate EG set that is the dx squared minus y squared and the dz squared orbitals. Now, if you put, say, 1 electron in it, then our atomic term would be doublet D, and it would split into 2 terms in the complex. If you put the electron in the lower set of T2G orbitals, we would come to a doublet T2G ground state. So we have a doublet state because 1 unpaired electron, and it's triply degenerate because the electron can either be here or here or here. So that's a doublet T2G set, and if we would move that electron over here in the higher energy set, that would be then a doublet EG state. So you see how basically the ligand field is splitting the Russell-Saunders terms of the free ions into many particle terms. Now I will very briefly show you, I only flash it up. This is some mathematics to that. And it may look a bit scary if you're not used to it. In terms of quantum chemistry, that is very simple mathematics. And it simply like goes through the electrostatic potential that is created by the ligands, and then it's going through some angular momentum coupling algebra to give you then an expression for that ligand field splitting in octahedral symmetry. And by convention, that splitting is called 10dq. That is completely historical. There is nothing you have to understand why it's 10. Then it's just simply by definition, it's called 10dq. And the mathematical expression for it would be 5/3 times q is, small q is a charge on the ligand, r to the fifth is the metal ligand distance, and then there is a fourth power of the distance of the electron from the transition metal nucleus and its expectation values. And you know what? You don't need to remember any of that because it's completely unrealistic. So if you would really take atomic orbitals and evaluate all these integrals and then put numbers in, you get ligand field splittings that are completely all over the map and have nothing to do with anything you ever observed. And that is what I mean by a model. So what we've seen now in the model is that the Russell-Saunders terms of the free ion split into many particle terms in the molecule. And what ligand field theory gets right is that this splitting occurs and it correctly predicts the number of components that arise from the atomic terms. However, no molecule ever works according to such electrostatic pictures. That is just simply absolutely and completely unrealistic. Yeah, and that means ligand field theory taken literally is unphysical. And ligand field parameters are therefore not theoretically defined, right? So when I said 10dq is the splitting between the T2G and the EG set, that's great. But as such, there is no way to really calculate that from first principles because it arises from a model that is physically unrealistic. And that means the only way to determine then these 10dq values is to fit them to experimental data. So today that's not true anymore. So we have worked very hard on finding a connection again between the first principles of physics and these ligand field parameters, and we have succeeded. But I don't think I'm getting to talk to you about that. So that means you have to have a means of measuring these ligand field parameters. And so since I said it's a splitting between orbitals, 10dq, what we have to do then is to move an electron from the T2G set to the EG set and then measure the energy that it takes to do that. And that, of course, is an optical absorption experiment. And very early on, it was quite successful because people predicted that for a D1 system, then there should be an absorption band that corresponds to the excitation of an electron from the T2G set to the EG set. And fair enough, in D1 complexes like hexaquo titanium 3+, you really have such an absorption band, and it's about at 20,000 wave numbers. It's an ugly absorption band, and it's split because things aren't quite as simple as I made them here. But we ignore that bump here at the moment and say we have one absorption band. The absorption band corresponds to the doublet T2G to doublet EG transition, meaning moving one electron from the T2G to the EG set. And hence, the value of our splitting that is 10dq or delta OH, if you want to call it that way, is on the order of 20,000 wave numbers. Now, of course, chemists absolutely love series of molecules, and for a good reason, right? And so when you say show that to a chemist and he said, okay, hexaquo titanium 3+, but what happens if I put a chlorine there? And what happens if I put a fluorine there? And what happens if I put a cyanide there? And so for years and years, people have busied themselves making all these compounds and measuring their absorption spectra, and that's beautiful. You see, that really is the nature of chemistry. This is how chemists' brains function, and that's a good thing that it's that way. So, and as a consequence, we have the spectrochemical series. The spectrochemical series then orders the ligands according to their ability to split these d orbitals into a T2G set and an EG set. And so we have here at the very low end of the spectrum, we have ligands like iodide or sulfide or fluoride. And at the very high end of the spectrum, we have NO+, NO, CO, cyanide, etc. So small deltas are occurring on this side of the spectrochemical series. Large deltas occur on that side of spectrochemical series. So if, like, we talk about the electrostatic picture, of course, that I've shown you, this outcome is really unexpected, right? So why would hydroxide be a weaker field ligand than water, right? So if really like point charges would be the source of the splitting, then you would expect that something that's actually negatively charged has got to be a more stronger splitting agent, so to say, than something that's neutral. That's not observed. And so you see even the strongest ligand that we know is NO+, right? That's not even negatively charged. So you see, like, already from that observation, you will have to discard the electrostatic splitting that I talked about as a source, as really the main source of the ligand field splitting. And that is so, and I will give you an explanation of what's really happening a little later in the talk. Now, in biochemistry, that has also been done. That is largely work of Andy Thompson from the 1990s. And so according to Andy, and he has used, I think, porphyrins with variable axial ligands to figure that out, the smaller field ligands are carboxylate, like aspartate and glutamate, followed by cysteine, followed by tyrosine, and at the high end of the spectrum are lysine and histidinate. But of course, the variability in nature is far, far less than the variability you have in synthetic chemistry. And it's still absolutely amazing how much chemistry nature can do with such an extremely restricted set of ligands. Now let's look at the energetic consequences of the ligand field splitting, and that is one of the major triumphs of ligand field theory. Oops, I think that is one too far. So the idea here is the following. So first of all, when you put the transition metal ion into a ligand field, all of these d orbitals get destabilized. But then the T2G orbitals get less destabilized than the EG orbitals. And that means, relative to the center of gravity, you can attribute the splitting of each of the three T2G orbitals as minus 2/5 over delta, the splitting, so 10dq. And each of the EG orbitals relative to the center of gravity of 3/5 delta. Now let's not make life too complicated. Let's just say, so whenever I put an electron into a T2G orbital, I gain a stabilization energy of 2/5 delta, and whenever I put an electron into the EG orbitals, I have to invest a ligand field destabilization energy of 3/5 delta. Now let's look here. That's a beautiful experiment, absolutely beautiful experiment. So these are the hydration energies of the divalent transition metal ion. So what people have measured here is the energy that it takes to take a naked 2+ transition metal ion and put 6 waters around them. Yeah, and so that is an exothermic reaction, and you can measure its heat of formation of the hex-aquo transition metal complex. And I don't know if what I would have done if I had been the PhD student to show my advisor this curve here. I said, I think something must have gone wrong there, and then here I'm not really sure, and there it's. I think to me that looks pretty much like a straight line, doesn't it? Then it's, and at least if I plot the logarithm of that, and you know how it goes, right? I mean, that doesn't look like something we would particularly enjoy. But now it's data like that. That's why it's so important to be honest in science. If we don't understand it, then we just don't understand it. And we put it out in literature to say, like, look, this is the measured error that I have, and here's my curve, and I don't understand it. And some smart person maybe down the road will figure it out. And in this case, it was the founding fathers of ligand field theory who have figured it out. So here we have our chemical axis going from calcium all the way to zinc. That means we have here a continuing dN configuration. Now, the overall trend of these hydration energies is that they get larger. And that is easy to explain, and that is so-called effective nuclear charge of the transition metal ion. So when we go from one element to the next, we add 1 proton and 1 electron. Right? And so the charge of the nucleus is getting larger and larger, more positive. And what is happening is that the additional electron is partially shielding the positive charge of the nucleus. But it's not completely shielding it. That means the water ligand that comes in from infinity that wants to bind to something positive is seeing a greater and greater positive charge as you move from the left to the right of the series. And that means the binding of the water to the metal is getting stronger and stronger. But superimposed of that overall trend of increasing hydration energies is that funky little double hump. And the explanation here really is the ligand field stabilization energy. And so you see that here the, the actual hydration energy is larger than what you would expect from the overall trend. And that is the reason for the first electron you have a ligand field stabilization energy of delta, then you put the second in, so you have that twice, minus 4/5. You put the third in, it goes into 30 g orbital. You have minus 6/5. But then you need to occupy the EG shell, and then you go from minus 6/5 to minus 3/5. And then when you have the half-filled shell, that would be manganese 2 plus, your ligand field stabilization energy is 0. And then for the second half of the transition series, you have the exact same when the first 3 electrons enter here, 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 and the last 2 electrons enter here. And so what people have done then is they have taken the ligand field splitting that they've measured in the optical absorption experiment, have taken that table here and have subtracted that ligand field stabilization energy from the experimental data to get that nice straight line here. And so that means, so we have the overall trend of increasing binding energies, but we have subtracted the ligand field stabilization energy to go from the experimental data to this corrected data here. And that made people believe, really, that ligand field stabilization energy is something that makes physical sense. And of course, it's one of those explanations where you have a funny-looking set of experimental data that turns into a perfectly regular, nice-looking set of data, and you have a good explanation for it. So that is then the story of the ligand field stabilization energy that is depending on the DN configuration. Okay? Now I will make it as far up to now life is nice and simple, and now I will make it gradually more complicated. The truth is, of course, electrons repel each other, and you might well say that almost 100 years of quantum chemistry have been an uphill battle against the consequences of electron-electron repulsion. But that is the case, and so 2 electrons, as they come closer, they will repel each other. And that repulsion is stronger when the electrons are closer on average. And it's kind of easy to see that if 2 electrons occupy the same orbital, that repulsion is very strong. Now, if 2 electrons are in 2 different orbitals and have opposite spin, and then they repel each other more strongly than if 2 electrons occupy different orbitals and have the same spin. That is something that is deeply quantum mechanical, and it makes no sense. There is no classical physics to explain that. And the explanation, the quantum mechanical explanation, is that there is an exchange, and that exchange term, I'm very reluctant to call it an exchange interaction because there is no exchange interaction in nature. But there is an exchange stabilization that favors parallel spin electrons over anti-parallel spin electrons. And that is the basis for Hund's first rule. Yeah? So if you have the same set of 2 orbitals, then the pair of electrons that have opposite spin are always less stable than the pair of electrons that have parallel spin. Yeah? Okay, and these are the consequences. And that means also the fact that this happens is the reason that a given configuration, so distribution of electrons among orbitals, produces several states with different energies. Now, in quantum chemistry, dealing with that electron repulsion is a major pain in the neck. In ligand field theory, it turns out it is super simple, because what ligand field theory has adopted is the theory of atoms, so the so-called Slater-Condon theory or the Racah theory. And so in ligand field theory, electron repulsion can be taken care of by just two parameters that are called B and C. These are so-called Racah parameters. So right now we have the one electron splitting parameter 10dq, and now we have the electron repulsion parameters B and C. And so B is roundabout on the order of 1,000 wave numbers, and fortunately it turns out that the ratio of C over B is always very close to 4. That means there only really is one parameter B that is describing all of these wonderful subtleties of electron-electron repulsion. Now let's look at an example here. So for example, in the D2 configuration, we have a singlet T2G state and a triplet T1G state. So the triplet T1G state is two parallel spin electrons in the T2G shell, and the singlet T2G state that comes from a paired set of electrons in the T2G shell. And so if you're educated in the math of ligand field theory, you figure out that the splitting between these two states here is 6b plus 2c, so it's the same set of orbitals. That means 10dq doesn't enter here. But still the splitting between these two states is on the order of 14,000 wave numbers, so that's still an optical excitation. And remember, these are two electrons occupying the same triply degenerate set of three orbitals, and the splitting between these states is 14,000 wave numbers. That is 1.5 electron volts roundabout, or more, 1.7 electron volts or so. So it means the electron-electron repulsion is really, really strong. It's very strong, and the splittings that arise from from those electron repulsion. So this so-called multiplet splitting between the terms arising from a given configuration can be very large. So that is not something that like, Mr. Theoretician is like nitpicky on things. This is really something that is absolutely fundamental in transition metal chemistry, and you have to have a certain appreciation for it. Now, that, of course, then means there is a competition in certain electron configurations between the splitting 10dq and the electron repulsion. And that, of course, leads to the entire subject of high-spin, low-spin complexes, and eventually to such technologically important subject as spin crossover compounds. So let's illustrate that with the D5 configuration. So it can either be a high-spin configuration where each orbital has one electron, always spin up. That will minimize the electron-electron repulsion, right? Because the electrons stay apart and they have the same spin. That's good. But of course, you pay the price that you lose the ligand field stabilization energy by occupying these high energy orbitals. Alternatively, you may pair up the electrons here all in the T2G shell. That's favorable in terms of the ligand field stabilization energy, but you pay the price of increased electron-electron repulsion. So at some point, there's got to be a situation when this splitting here is very small, the 10dq splitting is very small, this will certainly be more favorable, whereas if the splitting is extremely large, then this situation is more favorable. And both of these things are known, and it depends then on the splitting 10dq, which configuration is more favorable. Then, of course, that leads us back to the spectrochemical series. If we have ligands on the left of the spectrochemical series, we will form high-spin complexes, and if we have ligands to the right of the spectrochemical series, we will form low-spin signals. Yeah, so it's a ratio of delta over B. Yeah, so if delta over B is small, we have a weak field ligand and a high-spin ground state. If delta over B is large, and large means 20 to 30, then we have a strong field ligand and we have a low-spin ground state. So now everything I have said so far can be summarized in the most beautiful way in one set of diagrams where there is one diagram for each DN configuration. And these are so-called Tanabe-Sugano diagrams. So they're basically, that's the pinnacle of ligand field theory or crystal field theory, the way I've talked to you about it. And now these diagrams, you will find them typically in the appendices of inorganic chemistry textbooks. And so I hope that I have managed to slightly demystify these to you if you always wondered what these things are. So here on the x-axis, you're plotting delta divided by B. So that is essentially going from the free ion with a ligand field splitting of 0 all the way to strong field ligands. So and we're just simply using B as the unit of electron-electron repulsion. And here on the y-axis, you plot the energy of the given many electron terms that arise from the given Dn configuration as a function of that ligand field splitting relative to the lowest state. So that means you have here on the y-axis, you have the atomic spectrum. Yeah, so the Russell-Saunders terms that you will find in the Neese tables of the free ion. And then, of course, as delta increases, at first is 0. That means you're in the weak field limit here. And then the energy of the terms, they're changing as a function of delta. And eventually, not in all the n configurations, but in a number of the n configurations, there is a certain breaking point where the system transitions from a high spin ground state to a low spin ground state. Yeah? And so there is a break in these Tanabe-Sugano diagrams that look like a discontinuity. It only looks like a discontinuity because we're changing our reference point for plotting these energies on the y-axis. Yeah? So, but it's the energy of a given term relative to the ground state. And these are extremely powerful diagrams in order to understand transition metal spectroscopy. And countless thousands of spectra have been understood with reference to the Tanabe-Sugano diagrams. And that is why ligand field theory is such a beautiful model. So with a minimal number of concepts that I could explain to you in about half hour, then you have access to thousands and thousands of experimental spectra, and they're correctly described by ligand field theory. Now let's look at the Tanabe-Sugano diagram for D2 ion. So here we have again the ligand field splitting. Here we have the many electron terms. And so in terms of the Russell-Saunders states, the ground state is a triplet F. And we have singlet D, triplet P, singlet G, etc., etc. And you see how with increasing splitting, the energy of most of these terms just increase. And now, of course, you have to put a selection rule on top of that. And in optical absorption spectroscopy, transitions are very strongly forbidden if the total spin changes between the ground state and the excited state. That means since we have a triplet T1 ground state, you have to look in the Tanabe-Sugano diagram for excited states with triplet multiplicity. And so what you're finding is then a triplet T2 state, a triplet T1 state, and at very high energy, a triplet A2 state that's probably deep in the UV sun. That means for a given D2 ion, you expect just 2 absorption bands, and they correspond to a triplet T2 and a triplet T1 excited states. And that is absolutely the case. That is the experimental spectrum of hexaco-vanadium 3+, and it absolutely has these 2 absorption bands. And they occur with a certain splitting between them that is predicted by the Tanabe-Sugano diagram, and it's absolutely correct. So these relationships between the relative positions of these absorption bands, they're correct. Then you have these interesting set of states, a singlet E and a singlet T2, that are essentially independent of the ligand field strength. So what is that? So these are so-called spin flip states where you simply flip the spin of an electron inside the T2G shell, right? That means they're completely independent of what the splitting here is. And they are independent here. They are of singlet spin symmetry, so they will be very weak. But in certain spectra, when you have high resolution, you will find them at low energy. So somewhere here, there will be very, very weak bands, typically very sharp, and very sharp, very weak bands that correspond to these transitions. So that is great. And so that means in order to determine these ligand field parameters, all that you need is a ruler, so to say, and you need to apply the ruler and like move it back and forth until you hit the experimental positions of these 2 absorption bands, and then you know the ligand field parameters. And that holds also for very busy electron configurations. So the busiest electron configuration is the D5 configuration, so that leads to around 250 states that you can form from that. And so that's a very busy Tanabe-Sugano diagram. Now, let's look at the high spin side of it. So then you have the sextet A1 ground state, and that would be manganese 2+ or iron 3+. And obviously, you don't have any spin-allowed transitions here, because whenever you wanted to move an electron from one orbital to the other, you have to flip the spin. Otherwise, it's not possible. That means you only have spin-forbidden transitions, and it's true because you see here in the absorption spectrum on the y-axis, the extinction coefficient is on the order of 0.03 here. So these are extremely, extremely weak transitions, and most of the time these ions are colorless. So manganese 2 complexes are typically colorless. Iron 3 complexes are not because of metal to ligand charge transfer transitions, but manganese 2 is typically colorless. And so that means these extremely weak transitions here must correspond to sextet to quartet transitions, and see how easy it is with the Tanabe-Sugano diagram to assign them. So you have sextet A1 ground state. So the first excited state you hit is a quartet T1, that is this one. The next one is a quartet T2, that is this one. So the next ones are the quartet A1 and quartet E. So they're essentially ligand field independent, and you see that because here are these sharp transitions, that is the quartet A1, quartet E. And then you have another quartet E and a quartet A2, and that's it. So the Tanabe-Sugano diagram is such a fantastic guide to transition metal optical spectroscopy. And if you're really serious about the optical spectroscopy of transition metal ions, then the Tanabe-Sugano diagrams are your big, big friend. All right, now so far everything we've been saying has been in octahedral symmetry, and of course life does not only consist of octahedral symmetry, and it is very instructive then to go through the different ligand field geometries and ask ourselves what are the orbital splittings that arise in different coordination geometries. And this is where we start to make a connection to chemistry, as I will explain to you in a second. So we've seen that splitting pattern here, T to G, EG, in octahedral symmetry. Now let's remove one ligand here from the plus Z axis, then we go to a tetragonal pyramid. And what will happen then is that the Z square orbital drops in energy, and the XZ, YZ orbitals also drop in energy relative to the XY. Yeah, so that means we have this E set of orbitals lowest here, then we have the XY, the Z squared that can come down quite a bit in energy, and then the highest one, the X squared minus Y squared. Now let's remove a second ligand from the minus Z side, then we have a square planar coordination geometry, and the same trend will continue. The Z square orbital will further drop. Quite typically it drops below the XY orbital, but that there are both examples of either the Z square or the XY orbital lower, and the XZ and YZ orbitals will get even lower in energy. A totally different splitting pattern you get in a trigonal bipyramid, where you have XZ, YZ lowest, and XY and X squared minus Y squared, so two pairs of doubly degenerate orbitals, and highest in energy is the Z squared orbital. And finally, in tetrahedral symmetry, you have the exact opposite splitting pattern of octahedral symmetry with a low energy E set, X squared minus Y squared and Z squared, and in high energy T2 set, XY, XZ, and YZ. And I've drawn it deliberately such because in ligand field theory, it shows you that this splitting here for the same ligand field strengths, intrinsic ligand field strengths of the ligand, the splitting in tetrahedral symmetry is minus 4/9 of that in octahedral symmetry, so about half. And that means in tetrahedral symmetry, you basically only ever form high spin complexes, right? Because intrinsically the tetrahedral ligand field is so weak that complexes are basically invariably high spin. Now there are a few like oddballs that are counterexamples, but by and large, if it's tetrahedral symmetry, then your ground state configuration is high spin. Now let's put this more into practice to like make it less theoretical. So here are some spectra that Ed Solomon and his students have recorded a long time ago, where they've shown that ligand field theory is actually able to like experimentally give you insight in coordination geometry. And so these are all high spin iron 2 complexes in different coordination geometries, and these are low molecular weight, structurally crystallographically well-defined molecules. And so they've worked out the rules according to which that works. These are, by the way, not absorption spectra. These are MCD spectra, because in high-spin iron 2, the absorptions occur in the near-infrared region of the spectrum, which are painful to study by absorption spectroscopy in aqueous solution because of all the water overtones. In MCD spectroscopy, because it's a differential technique, that measures the difference in absorption between left and right circularly polarized light, you can get rid of these water overtones, and especially if you go to D2O, you can measure these spectra. And that's why MCD is a wonderful, powerful technique, and I think you hear about it later in this course. Now, for octahedral complexes, then you find typically two absorption bands centered around 10,000 wave numbers and split by about 2,000. And that is the signature of a distorted octahedral site, where the splitting here comes either from low symmetry or the Anteller effect, which I'm not going to talk about in these lectures. And that is simply the quintet T2G to quintet EG transition. So you have the D6 configuration here, high spin D6. There is one extra electron in the T2G set, and exciting it to the EG set gives rise to that absorption band. Now, for a tetragonal pyramid, the pattern is that you typically have one band at around 10,000 and one at about 5,000. So that is pretty close to the detection limit of an optical spectrometer. but 5,000, that's 2,000 nanometers, you can still measure that. So that's a pattern for tetragonal pyramid. For a trigonal bipyramid, you typically have one absorption band at 7,000 wave numbers, and then there is another one below 5,000 wave numbers. And for a tetrahedral site, you have a pair of bands at around 5,000 wave numbers. So these are the rules, and of course you can count the bands out, and you can give them names according to ligand field theory. And all of that works perfectly. And here's how you can make some biochemistry with that. And the example here is Racah dioxygenases, and these Racah dioxygenases, they have two metal sides. They have a Racah center that is functional in electron transfer, and they have a non-heme iron side that is responsible for the chemistry, and that is very much a so-called facial triad here that consists of 2-histidine and a carboxylate ligand, and this does the chemistry. And what these enzymes do is hydroxylation chemistry of aromatic substrates in the presence of dioxygen. So dioxygen, 2 electrons and 2 protons give you hydroxylated product. Now, let's study the MCD spectra of these enzymes. Now, and they have performed 2 sets of experiments in parallel. So first they have the holoenzyme plus and minus substrate. Now, these MCD spectra, they contain contributions from the non-heme iron active site and the Racah center. So in order to come to something that is easier to interpret, you want to get rid of the signal of the Racah center because you're interested in the active site. And so what you do here then is that you do a little bit of biochemistry, and you remove the iron from the active site. So you can do that with EDTA or with cyanide that will suck the non-heme iron out of the active site and will leave you with the Racah center. So then you can measure the MCD spectra of the Racah center. These are these here. Look interesting, but let's not get distracted. That is for another time to interpret that. And let's subtract the Racah out of the spectra of the holoenzyme. And what do you see then here? In the holoenzyme, in the absence of substrate, you have a pair of bands centered at 10,000 split by 2,000. That means spectroscopically you show that this active site is in an octahedral coordination environment. But now interestingly, as you have substrate binding, now there is a new band growing in at about 5,000. And so then you have a pair of bands here at 10,000 and 5,000, and that means you have the characteristic of a tetragonal pyramid. That means upon substrate binding, one of the ligands of the octahedral iron site has dissociated, and the coordination site is opening up. And why is that significant in terms of the mechanism? And that is something that is almost universally true in the landscape of non-heme iron enzymes if they react with dioxygen. If you have the resting state enzyme, it's 6-fold coordinate, so it's coordinatively saturated, and enzymes do that to prevent Fenton chemistry. So as long as there is no substrate around, you absolutely don't want to have dioxygen around to react with the enzyme and destroy it. So the enzyme is incredibly clever. It only wants to open up the dioxygen binding site if substrate is around. And so that is exactly what is happening. As substrate is binding, the iron side is going from 6-coordinate to 5-coordinate, and that is what you see in these spectroscopic experiments in the absence of dioxygen. Otherwise, you would set the reaction into motion, of course. And now, since the iron side is 5-coordinate, substrate is around, dioxygen can bind here, and then interesting things happen, and I think here the group at Penn State around Carson and Marty have contributed so much to our understanding what's happening then. And what's happening then is that hot species form, hot high-valent iron sides form that can be trapped and studied, etc., and they are able to attack substrate and eventually hydroxylate it. So there's a lot of very interesting chemistry happening here, but what I've shown you is how you can then use spectroscopy and ligand field theory to study these initial parts of that mechanism. And I hope it was convincing to you that it's incredibly useful to understand a little bit of ligand field theory to gain experimental insight into these things. So this was almost as practical as it gets. Now we return to the land of theory, and I will quote on Christian Klicksbühl-Jürgensen, which is one of the founding fathers of ligand field theory, and he said, "Personally, I do not believe much of the electrostatic romantics many of my colleagues talked about." The electrostatic romantics, that is what I've talked to you so far. I don't know how romantic you found it. Then if you didn't find it too romantic, I'm very sorry. So what he means with electrostatic romantics is that you can take this incredibly simple picture where all ligands are just condensed into point charges, and everything is depending on only the geometry of the ligand field. And that leads you far, but of course it's not the real picture, and people wanted to know more. And of course, Jürgensen, being an incredibly smart guy, he knew experiments that were conducted way earlier. And so here's a Nature paper from 1953, where people have studied the EPR spectra of a crystal of iridium hexachloride. And you might rightly say, what has that to do with anything? And but I will tell you what it has to do with anything. Carson, you stop me when I'm out of time, right? Yeah? Okay, good. Because I have a little more to go. And so what people have seen here in that spectrum is they expected hyperfine coupling to an iridium nucleus of spin 3/2, so 4 lines expected. But the experimental spectrum, which by the way is not shown in the actual paper, which is really bad practice because you've got to show your evidence, and it's right. There are many, many more lines there, and they have attributed that to hyperfine from the chlorine nucleus. And what that means is there must be a finite probability of finding the electron at the site of the chlorine. Let me explain that to you in a simple example that's easier. See, that is my spectrum, and I show it to you. So that is the spectrum of copper tetraimidazole. That's a compound that's so simple to make that even I can do it. And so that's the experimental spectrum. It's copper 2 complex. It's a very pretty spectrum. And it has here hyperfine structure, 1, 2, 3, 4 lines, fourth one you don't see, and that is hyperfine coupling to the copper nucleus. And it has that really, really pretty structure here. And by labeling the imidazole with 14N or 15N, you can show that this structure here corresponds, arises from the nitrogen nuclei. Now, of course, if you take crystal field theory and look at the singly occupied the singly occupied orbital, it's a pure metal dx squared minus y squared orbital, right? So there is absolutely no probability density at the site of the nitrogen ligands. And that means you can really not explain this part of the spectrum where there is hyperfine coupling arising from the site of the ligand. And that means you need a refined theory that includes the ligands explicitly. And they say, at this point, you say, sorry, our dear colleagues from physics, the world isn't a point charge. You need to go a bit more into detail. And that theory, of course, is molecular orbital theory. And in molecular orbital theory, you describe chemical bonds as forming between constituent atomic orbitals that interact with each other to form delocalized molecular orbitals. Now, here are the extreme cases of that. If you have 2 orbitals that are the same, so equivalent orbitals on different atoms, you form a so-called homopolar bond. And that means you form from a set of orbitals A and B a bonding orbital where these two atomic orbitals are in phase, and an anti-bonding orbital where these are out of phase. So here they have constructive interference, here they have destructive interference. Now, and if you have two electrons here, you can occupy the bonding orbital, and then you form one classical bond. Importantly, the bonding component is always less stabilized than the anti-bonding component is destabilized. That means if you have like 4 electrons and you occupy both electrons, both orbitals fully, the result is a repulsive interaction. That is the reason why like rare gas dimers don't like to form. Now the situation is different if these two orbitals arise from different types of atoms, and these orbitals are, the base orbitals are, the atomic orbitals are at different energy, and then you form a lower energy bonding orbital that is mostly reflecting the lower energy atomic orbital of the constituent, and the higher energy anti-bonding orbital that is mostly reflecting the higher energy component of the pair. That's a heteropolar bond. Then, of course, there is symmetry, and you have you classify these bonds in terms of sigma bonds, bonding, sigma star anti-bonding, pi star anti-bonding, or non-bonding orbitals that are lone pairs. Now, the definition of the bond order is then 1/2 the number of electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. It doesn't necessarily tell you anything about bond strength, but this is the formal definition of the bond order. Now, for transition metal complexes, it works the way that the energy of the metal d orbitals is typically higher than that of the ligand orbitals, and that means you form an anti-bonding component that is mostly of metal character, and an a bonding component that is mostly of ligand character. Yeah. Now, importantly, that bond is the stronger, like the smaller the energy difference between these two constituent orbitals are, and the larger the overlap between the metal and the ligand orbitals are. So these are the two factors that enter into it, the energy difference and the overlap. So now if you take a new look at the octahedral complex, you see it's quite a bit more complicated than what you had in ligand field theory. So there are many orbitals coming from the ligand, and then you have the 5 metal d orbitals. And you also want to take into account the metal s orbitals and the metal p orbitals that are empty. But importantly, you will find in such an MO scheme these 5 molecular orbitals that are mostly of metal character, and they're split in a way that is exactly the same as in ligand field theory. It's just now these orbitals are molecular orbitals, and they have partial contributions from the ligand. But everything else is the same. The symmetries of these orbitals is the same as in ligand field theory. They split as you would predict from ligand field theory. They will be occupied in a way that is consistent with ligand field theory, etc. But now, of course, they're embedded like in the rest of the electronic structure of the molecule. And that is way more realistic than crystal field theory. And so now we can go back to our EPR spectrum of the copper tetraimidazole. Now you see the singly occupied molecular orbital has a dx squared minus y squared contribution from the copper, but it has about 10% contribution from each nitrogen, and that accounts for that splitting. In fact, you can even make that semi-quantitative, because that splitting is proportional to the amount of probability density that is transferred to the nitrogen ligand. So that accounts successfully for most of the spectroscopic phenomena that you can measure on ligand field theory. Now, some people, and I'm not one of them, make a distinction between crystal field theory, that is the pure electrostatic picture we talked about in the beginning, and ligand field theory that combines the crystal field type arguments with molecular orbital theory. And this is John van Vleck, who was a big proponent on that. He also won a Nobel Prize for all of his contributions to magnetism. And he wrote something that I would never ever write in a paper. He said, in 1935 I published a paper in which I amplified and generalized the primitive crystal field theory of beta, blah, 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 and so on and so forth. So don't do that. It's not nice. Okay, so that's the last thing I probably should tell you, because I think I've probably I'm fairly over time. So now you can really understand the spectrochemical series. Now, and the spectrochemical series is really a series that is talking to you about pi bonding and pi back bonding. Now let's take a ligand that is a weak field ligand like chlorine, and so you see that the Eg orbitals, they're strongly sigma anti-bonding. So this is like the 3p orbitals of the chlorine, strongly sigma anti-bonding with the metal d orbitals. And the T2G orbitals, they're pi anti-bonding with the T2G orbitals of the metal. So everything's completely as expected. Now, the thing is, if you go to a strong field ligand like CO and you go to chromium hexacarbonyl, see that the Eg orbitals again are strongly sigma antibonding, but now something interesting happening here in the T2G orbitals, because now these are bonding between the pi star orbital of the CO. So here you see a pi star orbital and the metal T2G orbital. So, and basically the situation is then the following. If you have pi anti-bonding, so pi donor contributions from the ligand, what will happen is that the T2G orbitals are destabilized by the interaction with the ligand, and you get a small ligand field splitting. For a pi neutral ligand, the T2G orbitals are neither stabilized nor destabilized, so they're in the middle of the spectrochemical series. But for the strong field ligands, you have an interaction of the occupied metal T2G set with the unoccupied CO pi star orbital, and that will stabilize the metal d orbitals, and you get a very large splitting and hence a strong field. That is why NO plus is such a powerful ligand. That is why CO is such a powerful ligand. And that is also the reason why hydroxide is a weaker field ligand than H2O, because hydroxide is a good pi donor, whereas water is a bad pi donor. I think I've probably ran a fair bit over time. I'm very sorry for that, but I will stop here and hope that my story on ligand field theory was interesting to you. I don't know whether we want to do any questions, Karsten. And
questions would be absolutely welcome. I think
yeah.
the budget is for until 10 o'clock. If
yeah.
you wanted to, I'm not sure what's coming next.
Yeah.
Or maybe the
yeah.
series or the physical observation phase.
Yeah.
General thoughts. If you have a question, just ask your question.
Everyone's ready for coffee then. Have I lived up to a strategy then?
Well, there's going to be plenty of time to follow up with anything that you have questions about with Frank or others.
Yeah.
And I think we probably should wait for some coffee and then we convene afterwards.
Yeah.
Thank you.